industry, and not only in India, even abroad.
The Institute of Eminence scheme has been launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research institutions. IIT Madras is proud to have been selected as one of the select institutes of excellence. As part of our commitment to the cause of fostering world-class research, IIT Madras has set up a number of research initiatives in diverse fields of contemporary relevance. Many of these initiatives will go on to become centers of excellence within the IIT Madras system. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway. As part of these initiatives, it is proposed to host a series of webinars from each cluster to showcase the innovative research being generated to various stakeholders like researchers, industrialists, and policymakers. These webinars will give an opportunity to engage in conversation with eminent faculty from IIT Madras and other international researchers, and also to find more collaboration in those research areas. So why wait? Click the link below to be a part of this.
The one-of-its-kind microgravity drop tower enables experiments where space-like scenarios need to be simulated. And facilities such as these have enabled setting up of space.
Thank you. Thank you for the lovely videos, Shivram. And hello and good day to everyone. Thank you for joining us today. This is Rudra from the Office of Global Engagement, and it's my pleasure to welcome you all to the 59th webinar from the IRIS webinar series. So the Institute of Eminence scheme was launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research institutes. So IIT Madras is proud to have been selected as one such institute of eminence. A total of 68 research initiatives belonging to 21 identified clusters are presently underway at IIT Madras. So as a part of these initiatives, these IRIS webinar series aims to showcase the innovative research that is being generated to various stakeholders like students, researchers, industrialists, and policymakers. So today, from the Safety, Science and System Cluster, the research initiative that we are presenting today is titled Safety Critical Systems, led by Professor Raghu Prakash. So this proposed Center of Excellence will bring together experts from various domains of design, manufacturing, operations and maintenance, integrate the physics of probabilistic safety analysis, and use digital twin concept for individual asset management. So to introduce Professor Raghu Prakash, the speaker of today's program. So he specializes in the area of fatigue, fracture of materials, that is metal composite hybrids, and structural integrity assessment, remaining life prediction of critical components used in transportation, energy sectors, apart from new product design. Along with him, we also have Professor P.V. Varde, Professor J. Nijvik, Professor Oliver Starter, and Dr. Vikas Kumar Saxena joined as the speakers. So to introduce Professor Prabhakar, he is a professor of practice at IIT Madras and Raja Ramana Fellow, DAE, a former associate director, Reactor Group, as a well-known expert in the area of probabilistic risk assessment and its application as part of risk-based engineering. And we also have Professor Zezdimer Nijvik. He is the founder of MIRC Academy, and he is the creator of the MIRC Science, so which is a body of knowledge for prediction the time emerging performance of the given functionable system caused by natural and human actions. So we also have Professor Dr. Oliver Stater from the University of Kassel, Germany. He focuses on the analysis and evaluation of human reliability, the effectiveness of management systems, the safety and efficiency of complex systems, and the robust design of organization. And finally, we have Dr. Vikas Kumar Saxena, the former director and a distinguished scientist at the Defense Meteorological Research Laboratory, Hyderabad. And his areas of expertise are residual life protection, life extension of aircraft system used in Indian Air Force, and damage tolerant design. So it's my pleasure in inviting all the speaker of today's program. And we also have Professor B. Dattaguru, who has joined as the moderator of today's program. Well, he is a Padma Shri recipient, domain specialist in aircraft structures, aging structures, life extension methods, fracture mechanics, finite element methods, linear and non-linear, composites, smart structures, aircraft and missile design, and experimental stress analysis and non-destructive testing. So before we start, a note to the participant, please use the Q&A box to enter your question, and please like or upvote the question that may interest you so that the moderator can prioritize them. Over to you, Professor Raghu.
Yeah, thank you. So good evening and welcome to all of you. Are you able to see my screen?
Sure. Yes, Professor.
So I would like to introduce about this center, which is the Safety Critical Systems, and it is kind of proposed by me as the principal investigator with Dr. P.V. Varde as a co-principal investigator. Before I get into this, I should thank the Ministry of Education, Government of India, and then the Indian Institute of Technology, Madras, for having sponsored this Center of Excellence. As what you can see in this slide, we are being ranked the #1 as per the National Institute of Ranking of Government of India for 6 times. Okay, so before I move on, what's the background? What is, first of all, a safety critical system? A system whose failure or malfunction may result in death or serious injury to people is what we normally call as a safety critical system. And we can also see that there are cases where you can look at the loss or severe damage to the equipment or the property, or it could mean any environmental hazard. So there are several examples of the safety critical systems. One is aircraft. Of course, some of the panelists over here will talk about the interesting aspects for aircraft engineering. And then we have railways, we have automotive systems, and we have power plants. And the reactors can be a nuclear reactor, can be a kind of a chemical reactor, or any of those things, energy systems. And we also have the healthcare systems. In fact, recently we had this crisis with the supply of oxygen cylinders for the, the corona or the COVID-19 patients. So it was becoming one of the safety critical components of the entire system. So it comprises of hardware, software, and as well as the human factors. Why I include the human factors is that, all said and done, engineers are good at doing something, but that something has to be used by somebody. And somebody has to also have, in a different environment, he has to use it. So the usage in the hands of the user is very, very important for any system that we design. We may foolproof it, we may idiot-proof it in many ways, but ultimately it has to be used effectively in the hands of humans. So very often we also come across the human errors in the operation. So when we look at the structures or the systems, many of them operate over long periods of life. For example, a passenger aircraft may operate for more than 25 years. Some of the power plants may operate for 40 to 60 years. In fact, in India, under the new mission, we want to design power plants which can operate for 80 years or 100 years. So that means there has to be a lot of reliability and risk associated with the operation and the confidence level that one has to incorporate as part of these design and the solutions that have been provided. So how is safety criticality assured? It's a science that integrates inputs from various domains. Like, for example, from fatigue and fracture mechanics to integrate the durability concepts, from the field of the risk assessment in terms of probabilistic risk assessment, failure mode effect criticality analysis, fault tree diagnostics, etc. And in terms of user and usage profile. So these are 3 inputs that come in for the safety criticality assurance. So when we look at the life of a critical system, generally we call it in terms of two components. One is the calendar life, where the effect of environment comes into the picture. So there are cases where I might have bought an excellent airplane, but I might not have used it for a very long periods of time. Obviously, there are some materials which will age, deteriorate in their performance. So we need to look at that as one of the inputs from the calendar life section. And if you look at the technical life, that is based on mechanical loading or material degradation due to mechanical loading, or there could be an accident. And of course, there is now a recent, lot of emphasis on the maintenance, repair, and overhaul. So any system that what we design does undergo a repair, and then after the repair and overhaul, what is the revised life that one can expect becomes one of the important aspects. So when you look at the end user says, I need a system that meets my expectations at low cost of owning and has a high safety of operation, and it has to give me a very pleasing experience. So that means, all these qualitative treatments, when I do the actual objectives, it will be one of the most challenging stuff. And the end user also says that I want something which is specific to the system and not very general. So for example, if I have a kind of a disease, like for example, a cancer, I go to a doctor, and after he does the treatment, he gives you some assurance that you will live for some period of time. Okay, but that means what we are looking at it is individual centric solutions to the problem, yet a general approach to address all of the above concerns. So which is what we are trying to do through this center. And one of the newer concepts that we are trying to incorporate is the digital twin concept, about which you will hear shortly from Professor Dattaguru, who is also a moderator for this. And interestingly, Professor Dattaguru is just 80 years young. So he still has a lot of energy, and in fact, he's a good example for digital human twin for many of us. Anyway, so as what you can see on the left-hand side, you will see that it has been designed based on some models and based on some concepts. But when you put it into performance, you will notice that there are vagaries and variabilities in terms of performance and operation. So when you kind of integrate both this, for each of these systems, one would be in a position to say what is the kind of assured life or assured confidence with which you can operate these systems. So the Center of Excellence on Safety Critical Systems will bring together experts from various domains, like from design, manufacturing, operation, and maintenance, and integrate the physics of the problem and the probabilistic risk management, use digital twin concepts for individual asset management. We plan to integrate inputs from durability, reliability, and human factors to provide a comprehensive answer to the life expectancy. So the methodology is going to be numerical simulations and followed by experimental data, and then validation of results with the experimentation. So with this few kind of inputs that I want to share with you, I thought I will now pass it on to Professor Dattaguru. And if you have any questions at any point of time, you can contact me using the details given in the slide. I request Professor Dattaguru to speak about the digital twin modeling and also moderate this webinar. Over to you, Professor Dattaguru.
Thank you, Raghu. So I know Dr. Raghu Prakash as a very young student at the Indian Institute of Science. So I still like to look at him as one of my actual children who are already reached about 50 years and then going on. So I am very happy that you have a center of excellence on the safety critical systems is being inaugurated at the IIT Madras by the proposal of Raghu, and I'm so very confident under his stewardship the center will do outstanding work in the years to come. In fact, IIT Madras is also actually fairly close to me, and so many times I used to visit when I was a little younger. Of late, I don't normally encourage travel In particular, after the COVID has come, I virtually I said we are not actually moving out of our city as much as possible. But I'm sure, I think things will become actually normal, and we'll be able to actually meet more often in person. And I will see the Center of Excellence on the safety critical system to reach great heights at the IIT Madras. So, dear friends, I started looking at the digital twin. Of course, everything has a root. When I went to see my children, I was talking to people from the NASA, and then I suddenly realized that there is a lot of interest is being generated of the digital twin. And it's a time when I come and say about the digital twin, my close friends, very distinguished people, ask me, what is the digital twin? So it was in fact at such a situation. Then we started actually putting up, and after a couple of years, Aeronautics R&D Board was very generous to give me a project. At the age of 78 as a principal investigator, oh my God, it's really, I had to jump very high to see that. And normally they say only younger people can become a principal investigator, like Raghu Prakash. But they said, all right, at your age, we'll also give you a project as a principal investigator. So they have given, please put on my slides. And please put on, oh, you want me to share? Okay, share screen. How do I share my slides?
Ah.
Huh?
So
I don't see my slides. Are you able to see my slides?
No, sir.
No, Professor,
Sir,
like if you want,
if-
I can share from our end.
Yeah,
Ask
please,
somebody there to put it
yeah.
on. Yeah, ask them to put it on. No, there are only about 6-7 slides, not much. I'm not going to go on for very long. So can you put on my slides?
Yes, sir, I'm just sharing. Just give me.
Please put on my slides.
Naresh, minus up. Naresh.
Thank you. Dear friends, over years, I told you that we have been working with DRDO and ISRO. So we had actually a lot of practices in the Aero have been introduced into our work. We have done also how to check on the damage tolerance or whatever is the fracture behavior of some of the satellite launch vehicles, and also some of the missiles, some of the aircraft, also composite aircraft, delamination tolerance. So now with all that, once we came to the digital twin, we know that the digital twin has a wider application. There is no question. But I think it's a good idea for everyone to keep himself to a particular area in which he has been actually working over years. So we have decided that we look at what we call as the prognostic analysis of the aircraft, because you want to essentially find what is the residual life, what is the residual strength at any situation. Okay. May I have the next slide? So you see that an aircraft in the real world flying, my digital twin is the aircraft in the digital world. So we essentially make the digital twin of the aircraft in the digital world. And you all know that the black box in the aircraft keeps on actually measuring around 70 parameters, both for aircraft, airframe, as well as engine and the other performances. But we grab about, say, 20-25 parameters, which have actually relevance to aircraft structural integrity. And then we will try to put them on the digital world into the aircraft. All the aircraft one way. We also actually zoom onto important say, critical components, like I told you, joint, a wing root joint, wing fuselage joint, undercarriage fuselage joint, some of those important joints on which we'll zoom and put the loading onto that and see that whatever is the load, the flight data recorder records We underload and then put it onto this. Now, let us see the next slide, please. Why a digital twin? You see, it's because this is a digital model, that's fine. But the aircraft will be designed for a particular load level, which is actually prescribed by all the regulators and all that. But in reality, it may not fly at that load level. So you continuously actually monitor the aircraft and loads which are coming, so that you actually find actually what are the loads it's going through and what are the likely damages which can occur. This leads to what everybody calls not a scheduled maintenance, but a condition-based maintenance. Because the condition-based maintenance, the fellow who says the scheduled maintenance says, you again is to maintain it after 500 hours of flight. No, at the 500 hours of flight, I want to see at what load levels I'm flying. I may be flying at actually much at less level. I bought a car in the USA when I went there for 2 years, and it was a doctor, a lady doctor. She said, you see, Professor Dattaguru, I only just go to my office and come back at a very slow. So I found that her usage monitoring, if you do, the damage which she would have incurred is actually much smaller. Similarly for aircraft, even for aircraft, it not necessarily it actually flies all the time. The actual fighters sometimes fly at a much higher. Transport aircraft flies much less. Otherwise, the people like me at 80 actually will not have survived when we actually go in an aircraft. If they want to fly at the limit loads and ultimate loads, we are in great trouble. So this really helps to get into what we call as the condition-based maintenance. And I think the next slide. The next slide. So you just go back. Oh, sorry, this is the one. All right. So this is what it is essentially, because big data we keep on getting. Some of the people, they measure the flight data recorder 30 to 40 times a second. So you can see in a flight how much data they record. So from that big data analytics, and also to actually handle the big data, one thing like the digital twin, a finite element model, stress analysis, fatigue and fracture analysis, damage, crack growth, estimate remaining strength, remaining life. And the remaining life estimation use the fatigue curves and crack growth monitoring. Now we have the NASGRO, but we have our own programs also, because the NASGRO is all right for some of the standard. So we need to actually bring in the machine learning techniques, which now we are able to do. Next slide, please. So one of the important things, the next slide, is the structural joints. And that's where we do that. Bonded joints and the bolted joints. So what more it is, these are the ones which are very, 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 very critical. Next slide. The next slide, please. Also the bonded joints which occur at several places. Nowadays with composites, a lot of joints are made actually bonded instead of the bolted joints, or sometimes they put a hybrid joint, bonded plus. So bonded joints also became very, very critical with the composite structures coming in. And the next slide, please. The next slide. So I won't go further, I'm sure. I have actually given the message. The digital twin along with the machine learning techniques is used in our aerospace now to find out what is the remaining life, what is the remaining strength. To certain level of confidence level. It is a statistical learning, not machine learning. Statistical learning in the machine learning. And we are able to increase whatever is the expenditure in actually maintaining an aircraft. We know that there are actually many engineering fields. I'm sure several of them talk. Manufacturing. When I went to one of the seminars, manufacturing, everybody is using the digital twin. So the manufacturing, radar, the people nowadays have come up with how to monitor the radar. It is not the only one. You can compare actually Bradman and Sachin Tendulkar in the cricket, so that you can put their characteristics. So in aerospace, another where safety is actually paramount, and where actually damage initiation and growth becomes very important. So friends, it is going to be a very, very important thing in the safety critical system. I am very happy that Raghu has taken up using the digital twin concepts in actually many of the things we do. I wish him all the success and the Center of Excellence to really actually flower to a very great heights. So thank you very much. We'll actually start the presentations of others now. So I suppose I'm call upon or the Rudra will call upon.
Professor, you have to.
I can call upon.
Yeah.
I think next speaker is Dr. Vade. He has been already introduced. He is from Agile BRC. He is one of the most critical thing of the nuclear reactors. So obviously, his will be very, very interesting. On to Professor Vade.
Professor, to avoid the confusion, first of all, thank you, Professor Datta. Professor Raghu Prakash,
Yes.
to avoid the confusion, could you help me my presentation if you have with you, or otherwise I'll try from here.
One second. Did I pass on, Rudra, did I pass on the presentation of Dr. Vade?
Just
we
give me
can
a second,
put it up.
Professor.
We can put it up, sir.
Yeah.
Raju, I have shared Professor Tataguru's, Professor Vikas, and Professor Nesvik.
Okay.
No, if you have, otherwise I can start my.
No, I'll just put it up. I'll just put it up. Just a second. Yeah, there you go.
Okay.
Is it visible? Yeah.
Yeah, it's visible.
It is visible. It is visible.
So good evening, the board members. My topic is reliability analysis and probabilistic risk assessment for complex engineering systems. Because I come from the family of nuclear reactor and power plants at BARC. My operational experience has been around 36 years, 37 years, and risk assessment, of course, 25 years. So I'll be talking about complex system and then PSI methodology, what it goes. Actually, in between, I'll be turning probabilistic risk assessment and probabilistic safety assessment. Both are same thing. Because the risk assessment directly connect to the concern, I'll be using the word probabilistic risk assessment. Otherwise, in methodology and approach, both are same actually. So can I have my second slide, please?
Yeah.
This is a PRA, is a relatively new approach. The traditional approach has been deterministic. Why I am telling you how with the time we evolve, and as the data and modern technologies are available, our approach to everything that includes risk assessment also changes. And then we try to reduce the uncertainty, because you know that traditional systems, they were very conservative, a lot of safety margins. And as we go along, we know the material properties, we understand the performance of the system, we go on reducing that uncertainty, and finally we come to very compact systems and high performance compact systems. So this is a story all about this. And the traditional approach used to be having defense in depth. That means if one system failed, obviously when these systems were built in 50s, the confidence level was less, and the only approach was to have more margin, additional margin, so conservative approach. And defense in depth. If one system fails, second fails, third system. So that used to provide the kind of redundancy and diversity into the system. And I think it worked well. For almost like 60 years, it worked well, because why I'm saying around 430 nuclear plants were operating world over. And we have 3 major accidents. Okay, but nuclear industry cannot afford accident. So even these 3 accidents, they provided a lot of learning. This was 3 Mile Island accident in 1978, USA, Chernobyl in 1986, Russia, and then Fukushima, 2011. You would have all witnessed the kind of concern it raises and all that. But the spin-off of this was a very intense experience that we got, and then it was found that probabilistic risk assessment is an approach. If you see the PSA model of TMI, the accident which happened, that was predicted in the handbooks of PRA. So I think nuclear industry became more interested. And as the time passes, now probabilistic risk assessment has been occupying a very high dimension in terms of risk-informed approach, whether it is USNRC, UK as a safety assessment, this thing and all. And now you can say almost for all the nuclear power plant, PRA model is available, level 1 PRA model is available. That is something like a statement of how this approach is getting recognized. India also, the regulatory body, they will request you that before a startup is license has been given, you should have PRA level 1 at least, and over a period of time, level 2 and level 3. I'll come to what is level 2 and level 3. So this approach, because now we have experience, we have computerized model, we are able to talk about the PRA. But there are challenges, and that is why this safety critical system lab, we have to answer these questions in the sense that hardware reliability, there is an uncertainty, and that need to be reduced. Database is a little weak, and to capture the realistic scenarios, we have to do a lot of experiments with the data also. And that is where for mechanical component and for the solder joint in electronic cards, and of course power electronic cards, this fracture risk assessment is become a very, very important topic, because most of the electronics, they fail on solder joint failure, and most of the mechanical components, their failure propagation, especially when you talk about the material like stainless steel and high level steel, carbon steel and all that, you have to really predict whether we will have a leak before break situation, where we are able to predict that, okay, this is whether we are going to have prognostics, or we are reaching something like digital model, or digital twins actually, and then common cause failure. Even though you have a lot of redundancy in the system, there are events, whether environmental or operational events, they will lead to common cause. So your redundancy collapses there. Diversity. So you have diversity concept, but then at every level, seismic event, they can collect, collapse even your diverse system also. And then the third challenge, which is human reliability. A lot of uncertainty get introduced because of human reliability. And I'm happy that in Chennai, IIT Madras, we have under safety science systems, we have these two important things, that is safety critical system and one human factor engineering model. So there is a lot of scope to do experiments. And of course, advanced technology, when digital technology came, regulators will not give you clearance if you are depending only on digital technology. You have to have a analog system to show, to demonstrate the safety of the plant. So then application area, of course, there are a lot of applications, many of them. In fact, last week I was in IAEA, and India won over 1 point that for research reactor, only we have done risk-informed ISI. That means we have a PSA model, and based on that PSA model, we have developed a in-service inspection program which reduces the risk significantly, and it saves your time and efforts and all that. And it was a noting in IAEA that only India has done it, and the document should be developed on this. So these are something, you benefit you get across your technical specification, optimization, maintenance management, overall operation management, life testing and qualification. These are very important areas. Can we go to the next slide? Which will, these are a few I am noting here, but I have only 4 slides, so I will not take much time. Next slide, please.
Yeah.
Okay. So now, since this topic was probabilistic, and it is a very wide topic. In fact, if I put a PSA document in front of you, it occupies the whole dimension of my table actually. There are something of 5,000, 7,000 pages, and each is having 1,000 pages and all it. So it is a very, and it takes around 2 to 5 years time, depending on the manpower that you are putting into it. So it's basically what is PRA? PRA is, if all of you must be aware, fault tree, event tree, HAZOP, these are the techniques that are used, reliability block diagram. So these are the individual techniques that make up PRA model. And PRA model is nothing but it is an analytical technique, which is used to predict the accident sequences. So you can say 99% accident sequences you have predicted by doing the theoretical modeling and various paths and various searches and all that. and now you are confident, but accidents always have their way of coming. So those 1% should be looked into it, and that is how rigorously you develop the model. It depends on it. 80% of the volume of PRA is covered by fault tree, event tree, but the major component is data analysis. It takes 60% of effort, because if junk in, junk out, if you do not have a good data, then you will not be able to get a good prediction. So this is how it is. And typical procedure involves, first you have to predict what are the events that are possible in the plant or any complex system, and then initiating event, you identify the initiating event. Like suppose power failure is one of the initiating event, how it can disturb the whole plant, or it can destabilize the whole plant. Once you have initiating event, then you create the event trees. Event trees means I'll show you on this here itself. So because you can see, once you had the set of initiating event, you are able to create the initiating event tree. So event tree itself will be having a one book, which is running into one event tree will run into something like 30-40 pages and all that, and all possible combination will be in. Now, in every plant, there is a process system wherein the initiating event gets initiated, and the safety system which are sitting on the top. So this safety system, the fault tree methodology is used to develop this system. And once you have fault tree analysis, final result, it forms part of the initiating event tree. And then
Dr. Wade, you have 1 more minute, please. Please try to complete fast.
Yeah. Okay. So I think I'll take 2 more minutes at least. Yeah. So now the data collection, as I said, it is a very rigorous exercise. And once you have data, it is quantification. And this is a human reliability analysis. It is more of not an analytical exercise, but a science. And then common cause failure, as I said, you have to identify all common cause failure, uncertainty and sensitivity analysis, which requires a lot of simulation and Monte Carlo and all those methods, and then Bayesian updating and all those things, and simulation and results and documentation. And this particular thing, as I said, it takes almost like 2 to 5 years. And then you are assured, and you submit it to the regulators. And once the regulator endorses it, they put their seal, then it is used for developing certain applications. I gave example of many applications. So, and here you have uncertainty characterization, and then finally data, what you do with the data, Bayesian updating and all that. In one chart, I tried to show it. It is I have picked up from the web actually. So there can be a better thing to explain, but I think time given is only 5 minutes. So can we go to the next slide, please? Can we go to the next slide, please?
Yes.
Okay. So in our presentation, we were asked to include so I think this could be one very important component, that is reliability modeling, quality assurance, and then you can say the safety modeling, PRA and all that. Because nowadays every regulator and every environmental committee requires a complete model, because it is an integrated model. It is quantified, easy to compare with any other things. So I would say this would be one of the important component along with the live testing, because nowadays, whether it is quality assurance or it is predicting the performance of the component in the field, the environmental testing is very important in all that. And then in the line of digital twins, we need to develop physics of failure model. In electronics, there is a reasonable progress that has been made. In prognostics and health management, this is a true example of digital twin. This is PHM and POF is one, and the second thing is simulator. So plant simulator, just before retirement, I have developed a simulator for Dhruva reactor, and we do all sorts of simulation there, whether it is reactor physics simulation, whether it is process simulation, whether it is electronic simulation, failure simulation, all we do there. So it is very close to, I would say, digital twin thing. And then when we have these labs and all that, we can have this MTech and PhD programs. And of course, we can have detailed research areas in the area of physics of failure, PHM, risk-based in-service inspection, maintenance management. And of course, whether it is a design, operation, maintenance, any or regulation, the human is a common factor, common thread. So human reliability analysis has to go very deep. Today's model, they give a lot of uncertainty, and sometimes the uncertainty is of the level that whether to consider those results or not, it is a big question. as far as academics is concerned, propose courses on reliability and risk analysis, live testing, risk-based engineering, and many more. That will depend on very detailed discussion. And students can be exchanged between IIT Safety Critical System and BARC. As such, we have a very set program for PhD and MTech in HBNI and BARC, and there can be a good exchange because even in my group, I had developed 4 labs. One is PHM lab, another one is reliability lab, one is simulator, and other one is vibration testing lab. So probably there can be a good networking so that students can get benefited. And of course, one is that PHM lab where I have photon emission microscope. You can go into the microchip and see what kind of fault or the configuration is coming in. So with this, I would say networking could be a good answer among the institutions. With this, I complete my presentation and thank you for your patience.
So thank you very much, Professor Vade, for an excellent presentation about
Thank
the
you.
issues in the reactors. Now I call upon Professor Hezovic from the UK. Sir, please, you are from the MIRC Academy. So please deliver your talk.
Hello? Can you?
Yeah.
Hello?
Yes, we can hear you.
Yeah, we can hear you.
Can you see my slides
No.
Not yet.
now?
No, Professor.
How about now? Do you see
No.
the slides?
No.
Oh, wow.
Do you want me to put the slides that you shared with me?
That
Yes,
will be a good
please.
idea.
I mean, we have to have slides.
Okay. Rudra, do you have the Professor Hezovic slide?
Sure, Doctor.
I'm just surprised you haven't got them. Normally, I could get them.
JK.
JK, yeah.
JK, yes.
I'm just presenting right away.
Warm welcome from England. And as you can see at the first slide, is our the best one because the sky is blue there, which is not always. Okay.
Yeah, it's there.
Okay, thank you very much. Right. MIRC is abbreviation for Managing Industrial Reliability, Cost and Effectiveness. And based on that, we develop the science which actually enables predictions of the life behavior of critical systems. So straightforward, can you go to the next slide, please? Straightforward, we have common engineering knowledge comes from the well-established scientific disciplines. We have Newton's laws, we have Maxwell's laws, we have everything which generated mechanical, electrical, nuclear, aerospace engineering, successfully working for several centuries. And all these engineering disciplines are able to predict the performance of the system. On my slides, on the left-hand side, we have a jumbo jet. On the right-hand side, we have exactly predictions which are made, and every single jumbo jet delivered reaches that maximum speed, reaches that range, takes so many passengers, so many cargo departments, etc., etc. In essence, this is possible. So the accurate predictions of the performance of the future systems are possible as the mechanisms of functioning of safety critical systems are certain, time and location independent. Gravity is gravity, fatigue is fatigue, corrosion is corrosion, momentum is momentum, force is force. However, could you put the next one, please? Oh, well, why can't I do it myself? Right. So when the systems goes in operation, as it happened in aircraft, you can have nuclear power, you can have railway station, whatever you like to have it. We are actually measuring and monitoring the performances of those systems, but in service performance. So we learned that aircraft can fly 500 miles per hour. But for the operators, for the airliners, it's important how many hours is flying per day, per month, per year, per life, because that is Why we have systems? We have aircraft to fly from London to New Delhi, and that is 10 hours flight. How many flights of 10 hours can we do it in 25 years of aircraft, as Professor Prakash says? Well, the natural sciences, physics, mathematics, physics, chemistry, astronautics, thermodynamics, fluid mechanics cannot give us those answers, okay? So what we have done, we start actually studying the life of those systems. Next slide, please. Could I have next slide, please? Right. So the science which study that, we call it MIRC science, miniature science, as we created this academy, is actually a body of knowledge that explains and predicts time evolution of performances of safety critical systems by determining the mechanisms of all causing actions. I'm very sad that I cannot drive slides from here. You only have my PDF version. Basically, the bottom line here is the axiom number 1 of miniature science says a system comes into existence in operational states. So here we are at 0, system started existence. And if no undesirable effect happens, we will have that green rectangular all life for 25 years and happy faces. However, as the second axiom says, a system stays in the given state until compelled to change it by imposed natural or human actions. So all the systems born gradually start deteriorating, which actually in the cumulative sense is presented with this step function red one. If we do nothing, we wouldn't have flights anymore. We wouldn't have operations. So we perform the actions to restore the system in operational state. So these are the green, red, and green. So if you look at any instant of time, we have the proportion, the green area, which actually system is operational, delivering the function. And we have the red areas where we are doing some actions in order to restore the capability of the system or to make it safer or to be sure that the next step, the next flight will be safe, as our first presenter presented, showed with the digital twin. Can I have the next slides, please? The event which we looked, the causing actions which we studied are enormous. Here on these slides, you have only some of them, but you can see the variety. For example, we have frost damage. We have the rodent attack. We have unbalanced system. We have bird strikes. We have incorrect tension. We have frost damage. We have fatigue. We have incorrect rating. We have software error. We have poor electrical joint. We have solar radiation, typing errors, fatigue, oil saturation, bad weather, headwind. As we speak, there are 20,000 commercial aircraft in the desert storage. We have no laws of science which predicted this. What is happening with the system and the subsystem, with the fuel, with the contamination. And those are the parts of the life. Those have mechanisms which actually impact the safety operations of those systems. In essence, what we concluded that the mechanisms of operation, of in-service operation of safety critical systems are uncertain, time and location dependent. Professor Varde was talking a lot about uncertainty, about reliability and predictions, and that is what we study. So we try to analyze what's happening in life in order to predict it. Can I have next slide, please? Next one. Right. This is the last one. It's rather busy. but that's what it is now, I'm afraid. What we have, the system starts to operate at time 0 and operates for a while, and you can see this now broken line here. That is the classical reliability function, which is the probability of operating to certain time in the future. What we learn then, at any instant of time, if you stop here, this proportion operates, but this proportion, the proportion of the fleet, is already non-operational. So what's happened with them? Some of them are already been restored. Some of them are in the process of restoration. Some of them already failed, been restored, and are operating now. So when you put the whole picture together, we are getting this equation, which actually generates that curve. And that curve y of t, we call it functionability equation. And for every instant of time, we can calculate the probability the safety critical system is being present continuous tense, being in operational stage. And that is equal to 1 minus and the sum of the differences between, now 1, what is the 1? The birth of the system. For the birth of the system, we have the negative event, which puts system down, and then we have a positive event, which brings system up. So the life of the system is actually convolution of positive and the negative actions which impact the life of the system. And that is presented by the green curve. The beauty is now, the area under that curve, is actually the integral of functionability equation, and then give us the amount of the work which system will give us for the life of 25 years. So the miniature science, in essence, enable us to mathematically create the future life in respect to all operational events, from lightning and thunderstorms and tsunamis and the rest, to the maintenance events, full repair, partial repair, replacement, modifications. And all of that is part of this equation here, because these events are sequential to time. So life is irreversible sequence. Unfortunately, in natural sciences, if you go 10 miles per hour forward, and then you come 10 miles backwards, you could come back where you started. But in the life, you don't. In the next hour, you can't go back. You can only go forward. And this is what that graph is presenting. So in final, to save the time, could you get the next slide, please? If you are interested, all is documented in the book, which I started experiences 50 years ago, and now I'm presenting to you in 5 minutes. So that's the origin of the miniature science, if you're interested. And part of that is in the book, Risk-Based Technologies, which has been edited by Professor Prakash and Professor Varde. So I wish all the very best to the center. I would be delighted if part of our knowledge could support the rise and the generation of the work which you do. With that, I'd like to thank you and all the very best.
Mr. Dattaguru, you are muted.
Oh.
I'm sorry. So thank you very much, Professor Nedžević. So since we are at a short of time, I'll just call upon quickly Professor Oliver Slater, please.
Yes, hello and good evening to India from my side. And yeah, I also share my screen for my presentation. And I'm happy that I will able to represent the human reliability aspects for the safety critical systems. And as Raghu mentioned already, it's not that obvious that the human plays a critical role in system design. But if you look at accidents, basically, you very often see the human element in system design and in system operations. And I just put together 4 classical examples that you see here. Fukushima was mentioned already by Mr. Wade. That is a design and operations basically failure that happened there. In Chernobyl, we had societal and operational issues with the reactor protection system that was manipulated in that event. But it's not only in nuclear, we have also in other things, mainly in transport, a couple of accidents, severe accidents in rail-based. For example, here's an example from Germany a couple of years ago, where we had a severe high-speed train failure due to maintenance and testing issues of humans. And most prominent before the corona disease was a Boeing 737 MAX, where we had competition between Airbus and Boeing, and basically severe design issues that were related to the failures of the aircraft. So if you look at accidents, you see the human element. The question is, first of all, where are human elements in system design? And in system design, we distinguish basically the scope of human reliability issues classically by the so-called Swiss cheese model. And if you look at the Swiss cheese model, there are a couple of different influences from human elements in the overall system that we normally combine with critical safety issues related to human performance. Well, if you look at the right, there is an accident, and before the accident, we normally look at the operational level. That are the people who are immediately in the accident, for example, the pilots in the cockpits or something like that. But that is not by no means the entire scope of human reliability issues. You have certainly the maintenance level, what played a role in the rail accident that I showed on the previous slide, where you have maybe human errors in checking procedures or in looking at cracks in the material or something like that. These two are basically related to the technical system where the people are operating with. But we also have a couple of influences from the organizational and management level. The management level is a level that determines the procedures, the processes within an organization, how to handle certain things, how to deal with certain things. And the organizational level basically decides which way to go for management decisions, for instance. And the organizational level played a very critical role in the Boeing accidents because the board of Boeing decided basically to go this way, and therefore these accidents happened. Well, beyond the organization, we also look beyond that organization, since the so-called resilience thinking of human reliability, that we look also outside of organizations, so to the inter-organizational level. That's basically the one where the system design takes place, where other organizations, including also research and development organizations, design a system, design the functions that are then used by the organization in their operations. And even the rulemaking level, so the legal level, is also part of human reliability issues. If you have a wrong legal rule that has to be followed in certain organizational processes, you basically then have human issues related to the rulemaking level. So we call that a blunt end on the left-hand side and sharp end on the right-hand side. So we basically not only have to look in human reliability on the sharp end, but we have to also look at the blunt end of the system. Well, another important thing is, beside accidents and accident investigation, is to have a probability and a design of a system. And therefore to have a proactive prevention of human issues, human reliability issues. And here we distinguish two types of assessments of working situations. That is a task-related and the goal-related way to assess human performance. What is the difference between these two angles of attack to deal with human reliability? The first one is, if you look at the task-related way of human behavior, you look at the work as it is specified by the designer of the system. For the pilot, for instance, the designer has certain specified requirements that the pilot has to fulfill, and these are the ones the pilot has to fulfill to operate the system. You only look at the required actions of the system in this view, and if the person, the human, is not adhering to these required actions, basically we talk about guilt. So the person who is not working according to the required actions is then guilty of the failure in the system. And what we also use is barriers to prevent those things to happen. We have warning systems, alarm systems, and things like this to prevent humans to not adhere to the procedures. Classically, task-related behavior is assessed with a probability of 10 to the minus 3. So that is a fairly good probability. So the task-related probability is about this if you have trained and educated people. Completely differently is the view of the goal-related, and there you see on the left-hand side a classical picture that I did last time when I was in Chennai. You see a bicycle rider with gas cans. Basically, the system design allows him to take 6 cans safely through the traffic. You obviously see he has 8 cans on his bicycle. Why does he have 8 cans? Yeah, basically he can sell more, he can transport more efficiently, and he does not have to go through the traffic several times during the day, so he can basically save a lot of trouble and time. And these are typical goal-related aspects. And the goal-related aspect of human reliability looks at the work as it is done. So how the people are really doing the work, how the pilots behave, how the operators in the nuclear power plant behave, how a medical doctor behaves in a real surgery, and so on. And what we are looking there is the likely behavior of the human in the system. So to look at the different goals he has, and the can driver here of the bicycle, he has an additional goal according to safety. He has on top of that simply the goal to be more efficient and to earn more money. If you look at a human failure, a human error in the goal-related view, we don't talk about guilt anymore. We talk about a symptom of a system that is wrongly designed. So we see there is a conflict in the system, and we have to look at and better understand why the system is working like that. The critical thing of goal-related aspects is that barriers are basically...
Professor, you have 1 more minute, please.
Yeah, I'm finished with this slide, yes. So the critical thing is that barriers are circumvented in goal-related view. So if you see this mechanical barrier to safely wear the cans is then basically overridden. And we talk about a fairly high probability of failure. If you have a conflicting goal in the system, we basically only have a human reliability with a failure probability of 10 to the minus 1. And both views are then accomplished to have a better work design, to have better and more robust systems, and to analyze the human behavior according to that. Well, that's basically what I wanted to input, and I thank you for your attention.
So thank you very much. So Professor Strater, very nice presentation. May I now call upon Dr. Vikas Kumar Saxena to make his presentation, which is the last presentation.
Hello. Hello.
Yes.
Yes. Raghu, can you just project my slide? Professor Dattaguru, I have got 5-7 minutes to speak.
About 5 to 6 minutes.
Okay. So I'll be very brief.
Can you just
I'll not be putting my all technical stuff here.
Sir,
because
yes,
already you all spoken about
Vikas's presentation.
Yeah.
Yes, please. Yes,
Give me a
please
second,
put
Professor.
my
I'm
slide.
just
I'll put my this thing
Yeah.
off. Yes, put my slide.
sure. Just give me a second. I'm just opening it.
Okay, okay.
You start with a spelling mistake.
Yes, yes. Structure. No, no, I don't know. They have put it. It's not my name. They have put
I
it.
know, I know, I know.
Raghu's group. I am also saying Vicard. Okay, so first of all, till you do it, I want to tell you, first of all, at outset, I must thank Professor Raghu Prakash, with whom I have a long association of almost 3 decades, for inviting me to this inaugural event of COE of the Safety Critical Systems. I'm also fortunate to share this dais with highly accomplished fellow speakers now from the different parts of the world. Especially, I'm very humble with my damage tolerance guru, Professor Datta Guru, whom I have learned 1982s around my fracture mechanics. So it is from the Shishya to my guru here. I'm very honored. So I want to tell you, I have had the opportunity to start my career in DRDO, defense, as a very young engineer with the very young engineer as a structure integrity area as a learning basics. Now I complete almost 4 decades doing structure integrity only for defense systems and has the opportunity to apply those principles successfully to various defense platforms owned by such as Air Force, Navy and Army. During this span as a project director, myself, very young team of the researchers attempted to provide various end-to-end solutions which have been implemented on aging defense platforms such as aero engines, artillery, main battle tanks, ships, submarines, and all. I'm avoiding, I will just give you only one slide. And for the first time probably in India, such a massive attempt was made where R&D labs basic and applied research was transcended directly to defense services battlefield experience. We integrated DRDO, national labs, almost 4 IIT. I am very honored to say here, even IIT Madras was a part of this thing. Several government, private industries, certification, quality assurance, airworthiness agency. It was not an easy task to do structure integrity or defense platform, where at least there was full involvement of service officers in uniform, providing access to it mission testing, secret mission profiles, experimental aircrafts, artilleries. I'm thankful to various international collaborators like AFRL, US Air Force, Saffron, Rafael R&D Center, who helped me this work. So based upon my field experience, as I feel SI is structure integrity is not as simple as we normally conceive in our engineering education. In field, it is highly interdisciplinary, as other professors just not talked. Challenging areas are there. Right from, I call it graduation from level 1, level 2, level 3. Now everybody is talking about industry 4.0. That is nothing but digital twins also for the critical structures. So our experience that we started all at level 1, which was only possible for India's large aging vintage old defense platform. As you know, Indian defense has got a lot of aging defense platforms. I'm showing here tanks, engines and all. They all have left, as Raghu was telling. They have either completed their calendar life or flying hours. And if they are under use, you have to give the predictive analysis. So it is very, very difficult stack. So right from graduating from the level 1, going up to digital 4.0, it requires a lot of work actually. And if you are in aero engines, it is still very, very difficult task because you don't know any design data, you don't know the materials, you don't know the even design features. Putting a digital twin model for the any new aircraft and all, it will be easier, but it is very difficult. So as the time we say, Professor Raghu says, we'll have very focused webinars, but based upon my research experience, I want to tell you just second, Rudra, second slide, please. Yes. So in Indian defense, we have got several platforms like structures, missiles, naval, armors, combat vehicles, ammunition, aircraft, engine, hypersonic vehicles, radar. So everybody requires structure integrity. We are supposed to do all. But right now, I'm going to just concentrate only aerospace or aero engines. And just third slide, please. That is last slide only. Rudra. Yes, this speaks everything what I'm going to talk. Maybe we on each area we can have webinar. It puts it here. What we do, we are not talking about the system level here, right side, all the things here, but you have to look into the material degradation because if you take the engine or even the submarine or the ship on right side, The moment you put it, as Oliver says, that until you put into operation, it is not even functional. So the moment you put it into operation, materials start degrading from the rate one, and most of the design or structure integrity is done with the normally with the virgin materials. So damage prognostics, health management, very, very easy, very, very difficult area, very, very challenging in the lab. And many times this damage is recording is very, very difficult. So then mission profiles are very, very complex in this nature. Left-hand side I'm showing, they are not very simple to. Then if you want to go for digital twins, you have to go for signature analytics and other thing. And each signature data, if you want to go ahead with the AI ML kind of thing, you have to do which signature means what, that is major challenging. Then down, I have put in failure assessment diagram. So now we are attempting to put it a 3D failure assessment diagram, that is nothing but a dashboard for the digital twins of the defense platform. At the end, a operator is looking at only this digital thing, how safe is our from the missing cycles. So based upon my experience, I will throw today only collaborative this challenging area. First of all, for any vintage aircraft or anything what we import, it is very difficult to decode the design philosophy. Thermodynamic model of at the design points, material and virgin database, usage history, mission profiles of the aging safety critical vintage platform, whether it is overused, underused, as Professor Datta Guru was telling, it is very difficult to find out because you get the aircraft, you don't get all this data from the OEMs and all. Then inspection history and maintenance database is very much required. Then development of structure integrity, lifing models are required, and their validation and scalability, because most of these lifing models done at the lab, but how to scale it up from specimen to component structure level. Validation and simulation, loss of the constraint is there when you go to component. Service conditions are very, very complex in nature, and issues related to realistic accelerated mission test is a major challenge. So most of these things, lifing structure integrity normally is done with empirical equations. As Raghu says, we have to go for the physics-based models. That is the way forward for the prognostic-based digital twins. I want to tell it. That is what I have given the spelling here. I call it, I think if you can read the heading here, it is a digital twin based. And the challenges from level 1 to level 4 is that to just not only you have to do for the old structure, whether the structure is safe now, if it is safe, how much safe it is, how much safety reserve is left for the future, and under what mission profile it is going to be the safe. And if it is there, like aircraft, we say in terms of the Mach numbers, altitude, firing rates, explosive, in case of the guns and other things. So major thing is that based upon that, is it possible to have the safe inspection interval life based upon the crack growth kinetics. Kinetics of the degradation is very, very difficult task under hostile environment. And then you should know retirement for the cause stage for all these critical defense structure. Because what happens, safety, all the structure is going to degrade and fail, but accidents should never happen in defense. So safely offloading the platform without an accident, that is a major challenge. So that will inculcate the confidence in operators, pilots, etc., to operate of the aging platform, because aging platforms can make accident at any time. So it is very difficult area. So a lot of reliability and other thing comes into picture, as my previous speakers have spoken about this thing. Then comes AI/ML, artificial intelligence driven life cycle management of safety critical. It is very big area, but the sensor technology though is very mature, but sensor technologies for the defense platform in hostile environment is really very, very challenging. Look at the left side. I have shown here something on the, I think some sensors here. I tried to put into sensor, but I could not use a wireless sensor because I tried to record these sensors for the material degradation and at almost 800 degrees centigrade. But under that, it is very difficult to record. So you have to develop a very fast response, highly sensitive, electromagnetic shielded, highly secured wireless MEMS technologies for recording material degradation, capturing physics-based signature analysis, and then come out physics-based AI/ML-based predictive maintenance, safety, and reliability models. So failure assessment diagram, one of the things we have been using, though it has been used for pressure vessels, but equally, I think it works very well. I think it is one of the very potent thing I found. Put everything in FAD and brittle fracture, plastic collapse. In fact, now I am trying to make it a multi-dimensional FAD where we can have hundreds of the parameters put together and predict along the timeline slicing. Signature analytics is one of the things. And then with mission by mission, like aircraft, for each mission, you can do a kind of a remaining life assessment. That is very important. And now, as you know, most of the defense and all, we are having only traditional NDT methodology to detect these cracks. Here I am talking about the crack detection of up to 20 microns, 50 microns, 100 microns. That is how prognostic based, as Dr. Guru was telling, it works. So even those kind of NDT technologies are not available. So upgradation of the NDT to 4.0 standard implementation for inspection at repair, maintenance
because
basis.
now you should summarize.
Pardon?
You should now say summarize, I think.
Yeah, it is over. Just last sentence, sir. And why very high level of detectability of these cracks is required. So there comes the question of probability of detection. POD is very, very important. As somebody talked here, probabilistic structure integrity of the critical is very, very important. Because at the end, if you're not able to detect this, can you do any kind of the modeling, digital twins, if not able to detect during repair, it is going to disaster. So real-time DT evolution with very advanced physics-based models is the future challenge for all that. So with this, I think we'll end. I think for each one, we can have a webinar later and we talk a lot. Thank you, Professor.
I think, so thank you very much. So Raghu, how do you handle the 5 or 6 questions?
Yeah, I think we will start with one after another. So the first question is from Roshan Wani.
Okay.
Was asked whether can safety and fatigue testing be used in medical application. My answer is yes.
Medical application.
Yeah, the answer is yes. And then space research, yes, people are doing it. Automobile vehicle design, yes, again. Avoid breakdown, zero maintenance, 100% result oriented. Okay. Well, all these studies are useful for identifying the cause for the failure. And as long as there is no unexpected defects that are there in the material or in terms of stress transfer being very different, one could be able to predict this.
And you see very important difference between the medical and the metallic. The difference is there is actually recuperating in the human being. That is something which actually the medical people have to give an input. I don't think the mechanical engineers or aero engineers can bring in understanding of the recuperating unless the medical people are able to give that. How a human being himself actually puts himself back to the earth. Okay.
True. But I think the question, I don't know whether the participant is here. The question seems to be more from the medical applications. So if somebody is looking at design of a heart valve or some kind of replacement of a knee joint or something like that, in those cases we do the medical devices testing and in vitro and in vivo, and we should be able to give the answer to some of these problems.
I think we'll go for next question.
Yeah, next question is on are digital twins and simulations the same? I think Professor Dattaguru or
I think
because,
there are so many people have asked me this question. Is the simulations and the digital twin are the same? You see, the simulations have been done over some period. But in the digital twin, you go actually further. You also go into a probabilistic analysis of the things happening. You also think of something like a predictive method. I think in the simulation, people have not necessarily developed a predictive methods. So you make also physics-based models as well as the data-based model, because the database also gives certain amount of way in which it is done. So I would say simulation is the first step in a digital twin. The digital twin goes actually much further. Unless it's Vikas want to say something.
Okay,
Vikas,
so
you want to say, okay, all right, leave it.
So I think there was
anything I have to answer, Professor Dattaguru?
No. There was a question on what is the difference between digital twin and simulation.
Okay. Dattaguru has already answered because it
Actually,
has to have the predictive analysis available in that. Yes, digital twin is okay, but predictive analysis is very important.
I would add there. I would add there that simulation, yes, it is a. But just when you develop a simulator, what you say is you are capturing the plant model. So to that extent, it is a digital twin. Similarly, when you do prognostics, you will tell over a period of time what will be the behavior of the system that you predict, and then you plan the maintenance. Two things. But then when we talk about the digital twin, we really don't talk about the only processes or interaction, or you talk about even the single hardware component mechanical aspects, which is covered by physics of failure approach. So yes, we have, we can say yes, but there are little more like big data and those things, they are coming into the picture, which makes the model more accurate. Thank you.
Thank you. So next question is from Dr. R.C. Prasad. What is the role of root cause / fishbone / failure modes and effect analysis in safety critical system?
Okay. This question is for me, I guess. See, the PRA modeling is a very, very complex task, So many industries, what they do is they do failure mode and effect analysis. What they do, component failure. It's at level, at system level, and then qualitatively they provide the frequency will be very high, consequences will be low, and all that. And based on that, they will again create a matrix so that they can assign the risk. But when you talk about complex system, the FMEA may not suffice. Why? Because the human aspects come into the picture, which can change the system configuration, number one, and which can fail many, like common cause failure. That is very difficult to model in FMEA because the different system interaction, you are not modeling, you are picking up a component and you are providing one-liner answer in the row. But in PRA, when you develop the cut set, the combination of different cut sets, that may be software failure, hardware failure, human failure, or even environmental issues like seismic and all that you answer. So for complex system, truly it should be a PRA model, because even if you take, let's say, electronics, different combination of input might give the result in different way, which was not tested during validation and verification time. So even if you have one or two sequences left out, it can create problem for the aviation or aircraft, or it can create a problem for a complex system where safety is very important. 1 in 1,000 chance you cannot take, because it affects the whole industry. One event and it affects the whole industry at international level. That is the issue.
I think in nutshell, you're also saying that the interplay between the various components of the system needs to be considered.
And then I have answered the part question. Sorry, I'll complete that. I'm sorry, Raghuji, to interrupt you.
No problems.
So you asked about the fishbone diagram and all that. Absolutely right. What you do here in PSA or PRA, you give the failure mode and their frequency. But if you go deeper down, how the component is failed, that is given by the physics of failure, or you can say root cause analysis. Root cause analysis is basically at present this technique is more, I would say, in my personal thing, it is more abused than used. Why? Because many times a brainstorming, 4 people will sit and they will, at the end of the day, when it is time to go, then they will say, okay, you assign this reason, human, and 90% they will put on human. Okay. You have a thing called physics of failure, where you really do live testing. From there, you try to understand the failure mechanism. You see the effect of various parameters, and that is where you develop a proper fishbone diagram and all the tools, whatever you may call that we use in root cause analysis. So in the root cause analysis, which I have developed it for nuclear plants, there I call level 1, level 2, and level 3, because practicality of the issues also should be taken into account. Sometimes you want an answer in 15 days time. So that what you do is you understand the direct cause, and then little more exercise you do provide the result. In level 2 root cause analysis, you go into testing, that simulation also. And in level 3, you develop really a physics of failure model and testing. But the level 3 takes around 6 months to 1 year. level 2 takes around 2 months, and level 1 takes around 15 days. So you cannot do a level 3 for all the failures. You have to go for, depending on the situation, consequences and likelihood of that event, that risk which was there coming with the event actually. Thank you very much.
So thank you, sir.
Thank you.
So I think
Raghu,
next
I may
question,
answer a little bit, just
Can
two
you
lines
please-
I'll speak.
Yeah, 2 lines. yes.
Dattaguru, because he has got very good nuclear experience. I'll tell you in our Indian Air Force experience, whenever such accident is there, we have taken data from Indian Air Force for last, you can say, so many years we have got data, and we take all maintenance data available. And then whatever is there is a physics of model. We know the conditions, we do complete mathematical simulation, CAD model and try to find out the physics of the model and try to develop that lifing model under real, in those conditions. And then we apply, because the root cause is available. Sometimes it may go wrong actually, most of the time. So collection of data from the maintenance command and the Indian Air Force and all head office, it is very, very important. So this is the same thing what Professor Vade told. Thank you.
Excellent. So thank you. Thank you.
Thank you.
Yeah, so Raghu, go to next question, please.
Yeah, next is real-time safety and reliability analysis feasible economically, as it might need significant instrumentation, capital, and computational investments?
Yeah, I think again this question is to me. The risk analysis, or rather probabilistic risk analysis, is a very complex exercise, because I have shown a very simplified version of this one, but it requires one expertise in human reliability, in PSA modeling, in probability statistics, plant operations. Let me tell you, if you do not understand the plant operation, then your PRA model will not be correct. So it is very resource intensive, but you can also see from what I said just now that all the 430 or 450 nuclear plants operating world over, they all have PRA model. What I'm saying is, if the system is financially very critical, that means if you shut down for one day, the losses are in crores or something. So whether it is a maintenance effort, operation effort, you create a PSA model, and from there you try to model your different whether in-service inspection program or any other tool, advisory systems and all that. But for simple system where you do not want to put much resources, I think process industry, they are very complex, but still I would say they are still following that HAZOP and failure mode and effect analysis. Probably that is relatively less intense. I mean, somebody can argue out, okay, that is also, it takes time and all that. But to me, it looks, you can have those kind of exercise. Or suppose if you have your motorcycle, and if you want to do a risk assessment, then you can go for FMEA, failure mode effect analysis, accident possibilities and all that, brake failure, this failure. So depending on your, what is at stake, commensurate to that, you put resources, and probably you can live with those resources and you will get benefited. So at least from 0, you will go to 50%, 70%, some improvement. Thank you.
Okay, sir. Thank you. You have
I think there's a last question.
Last
One from, I think probably it links to Professor Nesevic's graph, where he talked about probability of operation versus the work and all those things. So shouldn't the curve shoot up from 0 up to show its successful start?
Professor Nezovic, it's a question for you.
You are muted. You need to unmute yourself.
No, I am not muted. He is muted.
No, Professor Nesevic is muted.
Thank you.
Professor
Thank you for the question. The answer is absolutely yes. And I tried to make this with my slides, but unfortunately, as my slides were not animated, I wasn't able to present it. Absolutely true. It starts from 0 into 1 is the instant impulse. And from there on, operation and deterioration starts. That's enough.
So thank you.
Okay. So thank you. No more questions.
Over? Well,
Yes, no more questions.
So can I summarize that?
Yes, please.
Okay.
Yes, please. Yes.
So dear friends, you'll all agree we had a good feast of technical discussion, presentations, discussion on the area of the safety critical systems. Well, I would like to only call it a safety critical structures, but I know it's not only structures, there's also systems. which is more important. And out of which the structures is a part of it. Okay. We had excellent presentations from Ajit Professor Wade on the PRA, on the risk assessment systems and the reliability. I think he seemed to have actually worked in this area and submerged himself in that area. So we could see the way he actually enthusiastically actually presents as well as actually answers. I think he should have been a professor even from an younger age. I think he was in the wrong place. It was excellent, sir. We really enjoyed your presentation. Well, we have from actually UK, Professor Nitzuvik, very good presentation. A lot of it is with respect to aircraft. MIRCE, that's very good. Predict time emerging performance. That is something absolutely emerging. I think the predictive methods have now become very, very important in every field, wherever we see. I think the deterministic and the whole presentation, I think are now are left with our grandparents. Okay, so I think now it has come to the younger people who want all actual predictive methods. And thank you very much, sir, for your excellent presentation. Professor Setter from Germany, he has really brought out something which we never actually dealt with. That is the human element. That is something very important. Of course, I have conducted a workshop on the aviation safety 2 years back. We wanted to conduct an international conference, but the COVID has made it extremely difficult. In that workshop, several accidents, actually the people say now, the structures, people have understood very well. The amount of accident due to a structural failure have decreased because the people have actually beaten that field to a complete understanding. I won't say that, to people understand. So, it is happening now, the accidents are more because of the human aspects in the aviation. In fact, there were several, actually pilots have come in and also people who man the airports, they have all come to see how the aviation safety has issues other than just structures and the propulsion engines and all that. That's one thing. But there are actually a lot more issues to make aviation. So I think the human element is a very, very important thing by Professor Setter. Vikas, of course, he is actually known to us from a very long time. Dr. Vikas Kumar, he was the director of the DMRL and has actually performed to the hilt. And he works so closely about the life extension method, which is also very close to me. Of course, I spread a lot into various things, other things, and out of which the life extension method is like one part. But he virtually took it as his actually major expert. And Dr. Vikas Kumar has lot of information about the life extension method with respect to how it helps people. Anyway, Raghu, I'm sure that you have actually started very well in this Center of Excellence. I really wish you all the best. I think you are having at the right place. I think IIT Madras has fairly a good number of people who are actually working in this area. I'm aware of that. Though at one time it was actually more at Bangalore. I think now also the Bangalore is still one of the hubs of this area, with NIL and ISC all being there. But IIT Madras has developed into one of the major. I wish you all the success. I think please actually perform very well. If possible, here and there also include us in some forum. Either to review or to talk. We look forward to be with you.
Right.
And then we'll be very happy. So, wish you all the best.
Thank you.
And also wish the IIT director who has been here, I think, for some time.
Okay.
I know him also very well. So it's very nice.
Yeah.
So I would thank all the speakers who have taken their time off and have presented excellent presentation and made this a grand start for the Center of Excellence. We can tap it for that.
Thank you.
So Raghu, I expect you to have the focus seminars on the different areas in the future.
Sure, we'll do
One
that.
day seminar, I think I'd like to talk 1 hour like that.
Sure, no problems. So this center of this kind cannot sustain without the, the support from the peer group as well as from the well-wishers. and we also need quality students who would be interested in this. So on behalf of the Center of Safety Critical Systems, I would like to thank all the attendees of this webinar. And if they have any kind of interest and any specific questions they want to get addressed, they can always contact me or the other plenary speakers of this webinar. So with this, I would like to thank all of you and formally close this webinar.
Good.
Thank you very
Bye-bye.
much.
Thank you.
Bye-bye.
Thank you,
Have a nice
Professor.
time. Yeah, thank you. Bye.
Thank you.
Thank you, friend. Yeah. Rudra, thank you, please.
Thank you.
Good job.
Thank you, Professor. Thank you. Thank you so much.
Thank you, Professor.
We will sign off.
Yes,
Yes.
Professor. Mr.
Sign off.
Naresh, you can proceed
Before-
for the closure.
Oh,
Can,
Naresh has to.
closing?
can I just
sorry.
ask you a
No,
question?
Professor.
I'm really